about 10 lakh rupees at least, and each of those boxes will cost you a few thousand rupees. So clearly something which is, in the Indian context doesn't make a lot of sense. But the technology trend is definitely going towards doing more nucleic acid measurements. Now I'll switch gears a little bit to talk about microfluidics, and all the profs in the room, please forgive me if this is all too basic, but I thought it'll be good if some of the students actually know a little bit about how microfluidics developed. And really it goes back to the inkjet printer that many of you take for granted today, which is developed by Hewlett-Packard almost 50 years ago. And the resolution of an inkjet printer, that is the fact that you can see very fine text on it, depends on creating very tiny, precise picoliter droplets. So if you went inside and looked in a microscope, it's constantly spitting out a stream of very, very tiny droplets that are picoliters or pico to nanoliters. And to do that, you need very small microscale nozzles. So actually HP kind of produced the first precisely made nozzles about 50 years ago, and in some sense that's the first time you can say really a microfluidic technology was developed. But then of course there's a lot of dormancy if you see in my time chart here, and there was a whole electronics revolution which happened through the 1960s, 70s and 80s, which you see all around you today. And what that resulted in was people in about 80s started looking at making gas chromatographs, which are basically instruments to measure the components of a gaseous mixture using silicon features. So usually gas chromatographs are fairly large things, and somebody built it with silicon with these really small features. And then there was a general move towards this so-called micro-total analytical systems, miniaturizing a lot of existing analytical technologies using silicon and glass, which are of course well known in the semiconductor type of industry. But these are expensive and they're not so easy to make. And really what caused, I would say, an explosion in this field is something called soft lithography, which is the use of a casting soft material called PDMS, where you have a master. I'm going to go to the next slide and show you what that is. So all you are doing here is basically you first need to create a master, which looks something like this. So here it's a simple array of posts, and you can see these have features in the micron scale dimension, so sub-millimeter. And then you pour this liquid called polydimethyl siloxane, PDMS, and then you cast it into a rubbery solid, which you can then peel off. So this is extremely easy to do. Any of you can set it up in a day if you had access to all these materials. So this has caused, I would say, a huge explosion in academia, at least, in using PDMS, which can make remarkably fine features down to even the nanoscale. So that's PDMS. And what can you do with that? So this is really a lab on a chip concept. And what this is think of a big chemical industrial plant with all sorts of smokestacks and columns and reactors. And the big vision really of microfluidics is, can you take all of that and shrink it down to the size of a credit card, but still have a lot of those functionalities in it. So there's three things that microfluidics does for you. One is miniaturize, which is fairly obvious in saying, and really where miniaturization is important is in analytical applications where you have precious sample volumes. So not something like making paint, for example. Microfluidics would be probably a bad way to make something like that in bulk quantities. Then you have integration, which is basically all of these different things, separation, reaction, incubation, all of those integrated into one chip so that you don't walk around different places. So the vision of all of you, when you imagine a biology lab, right? What is the vision that comes to your mind? All of these people in white lab coats running around busily with pipettes from one station to another, transferring liquids and so on, right? At least that's the vision that comes to my mind. And what microfluidics is trying to do is basically say, look, let's shrink all of that into one small device and yet retain all of the functionality of it. And finally, automation, so that you don't have too much manual work and that reduces the scope for errors. So this is broadly what microfluidics is trying to do. And just like any other broad technology area, you have platform level work, you have component level work. So for example, building individual micro pumps or micro valves, and finally you're looking at different applications. So just to give you some examples, the simplest example actually is a home pregnancy strip. If any of you have seen these rely on capillary driven flow, that is wicking of a hydrophilic material. So you put a sample of urine here. In fact, what really popularized the home pregnancy test was home pregnancy. Yeah. So the fact that you can do pregnancy measurements at home, and this is about the mid 80s, I think, that this happened. And of course now it's really a product that's available at any pharma store for about 50 or 60 rupees. And then you have more sophisticated systems developed through microfluidics in the last few years. So for example, this is something called large-scale integration. So you've all heard of VLSI. Microfluidics is still kind of LSI, right? You can't cram in so many individual operations yet. But so this uses the PDMS valves, I'll show you what those are in a second, to make these microfluidic chips that have huge arrays of features on them. Then you have centrifugal microfluidics, which here again you can see somebody taking a finger prick of blood and putting it onto a small plastic CD-like material. And the idea is you use centrifugal forces to actually drive a fluid. And you have these centrifugal readers all around you. Basically any CD drive could do it. So this is another interesting concept. And finally you have these droplet microfluidics, where I'll just play this little video. The idea of droplet microfluidics is that you have two phases. So this is a continuous phase, which could be an oil, and these are aqueous phases. So imagine this is blood and two different liquids, right? You could form droplets of blood plus these two liquids in these droplets. And each of those droplets is probably a few nanoliters in size, so very, very small volumes. And the exciting thing about droplet microfluidics is that each of those individual droplets could be used to do a different reaction. So for example, you could change slightly the flow rates of these two phases, which means that you will have slightly different compositions in each of those droplets. And then you can study, for example, a parameter space, right? How does salt concentration affect protein precipitation? You can do thousands of experiments with a very small volume of liquid. So that's kind of the power of microfluidic approach here. These are microfluidic components. Here's a very simple example of a microfluidic valve where you have flow through the semicircular cross section into the plane, and then you have another channel built on top. The idea simply is that PDMS is a soft flexible material. So if you actually pressurize it, it will compress that flow channel and act as a valve. So it's like a pinching kind of effect. It's a very simple concept, but works pretty nicely. So that's what's integrated into this large scale integration that I showed you. One of the problems in microfluidics actually is mixing at the micro scale, because you only have mixing through diffusion. There's no turbulent flow at these length scales, with liquids at least. And what you find here is interesting architectures to do chaotic advection. This is simply, I think the best example is, you all know, to mix atta to make chapatis, for example, how do you do it, right? You have to like bend it, fold it multiple times in order to mix it. So that's kind of what you're trying to do at the micro scale with this sort of a micro mixer. So all of this is great. What is Achira doing? The problem that we are really trying to tackle is the lack of access to specialized tests in the doctor's office. And if you look at either the doctor's office or small labs in India, the way the Indian lab infrastructure is, there's about 100,000 labs in India. That seems like a lot, but only 200 of them are accredited by the national body, the NABL. The rest of them are like your neighborhood, kirana shops basically. So they do mainly blood collection and a little bit of very simple testing. And all of your sample needs, all of your testing needs are actually outsourced to larger labs. And the reason that happens is actually very business model driven, because the large instruments that are available, which are comparable, say, to the mainframe computers of the past, are fairly large, room-sized, bulky things like this, which can cost at least 10 lakhs, but can do fairly sophisticated, high-throughbut samples, have good accuracy, and so on, but are really suited to a context where you aggregate a lot of samples. So the result is that a big company will go to a lab and say, look, if you guarantee me about 2 to 3 lakhs a month of business, of basically of those reagents, then I will give you this thing for free. So the result is that you can't, being a small lab or a doctor's office, really afford to buy something like this. So you, by nature of the business model, you send the sample out to somebody else, right, who has one of these to do. But because of that, there are a number of things that happen. There is delayed results. There is problems with storage and shipping of samples, for example. There are emergency cases where you just need to know the answer right now. So all of these things mean that we need new technologies that can tackle some of these problems that I just mentioned. And there's a nice acronym that WHO came up with about what is the sort of technologies that we're going to need to overcome some of these problems. And some of the problems I've listed are here. So one is, like I said, the fact that we know a lot of biology today means that one test doesn't tell you the whole picture. You need to do usually an array of tests. One interesting problem which has come about is that in India, very often the cost of diagnostics is more than the cost of drugs. So in a small place, a doctor will quickly size up a patient, and doctors have an interesting job to do. It's not just based on medicine, it's also, they have to analyze, say the affording power of somebody. And if they feel that, look, he can't afford this 500 rupee test for malaria, but there's a 20 rupee drug, so why not just give it to him? Maybe we don't know for 100% that it's malaria, but we'll try it out. And then he comes back next week, and then we'll give him something else, right? So this actually happens a lot. And because of that, we've developed a lot of drug-resistant strains, which is very, very dangerous, because in certain critical diseases like malaria and TB, we're actually running out of options because there is a significant number of people who don't respond to the existing drugs. And I think availability of more affordable diagnostics could help in this problem. So these are all of the things that you need. Affordable is, of course, in India, I think that's very important. Sensitive and specific. Sensitive simply means you need to be able to measure really low concentrations of analytes. Something like glucose is an easy measurement to do. There's a lot of glucose in our bodies. But there's a lot of hormones, say, which are in a pico to nanogram per ml kind of range. So those are not easy to do. And then I'll just go over one or two of these. User-friendly. You really want the sample in, answer out capability that I talked about. And ideally tied up maybe with something like mobile phones even to quickly transmit data to a secondary health center. So this is the platform that we've been developing the last couple of years, since 2009, where you have a microfluidic chip that looks like this. You can see there's two ports here. One is a sample entry, and the other is for some wash buffer. So the chip will come loaded with wash buffer, and all a user will have to do is put in a sample of blood here, and then load this chip into a small desktop instrument, which will then be able to give an array of different results in 15 to 30 minutes, depending on the particular panel. So there's a definite simplicity of use and ease of workflow. You can actually customize the cartridge to do single sample or multiple sample, depending on the load. And the nice thing is all of your reagents are self-contained in the chip, including, and finally the waste is also self-contained. So you can just throw out this chip once you're done. And this is a small animation of the what the chip looks like. So you can see that the active elements actually of this chip are these hydrogel-based sensors that are here. So each of those hydrogel sensors that's actually trapped inside the chip can do a different immunoassay in this case. And as the blood flows through the microfluidic chip, it actually attaches to these hydrogel sensors. There is also a detection reagent which is then follows this and then leads to a fluorescence-based detection, which is basically a light signal that can be collected from those different spots to actually measure what the analyte concentration is. So one little link that I wanted to bring about is many times you all wonder whether what you're doing for your project work or your undergrad classes or your PhD is actually ever going to be useful to anybody, right? That's also an existential question that you ask yourself. And I think, in my case, I'm pretty fortunate that something that I did for my PhD actually is something that we are routinely using in the company and which actually is proving to be very useful. And this is simply this microparticle fabrication technique that I'm showing here. And the idea simply is that you actually use microfluidics for a synthesis application. So here in this case, you have a microfluidic device and you're able to, in a very high throughput form, make these hydrogel particles. Hydrogel is basically a cross-linked polymer which is an aqueous, which is made from an aqueous prepolymer mix and is very friendly to biological materials like protein or DNA. So you can make a lot of these particles, and each of these particles can contain different reagents and is then loaded into our chip to do these multiplex tests. This is just the insides of our reader. So the idea, of course, like I said, is you load the chip into the reader. Then the reader is able to interface with the chip and do all of the pumping operations, which are microcontroller controlled. And then there is a fluorescence detection scheme which is built underneath that is able to go and read an array of spots and read off the levels of your analyte and compare it to the calibration curve that's stored inside. So one of the nice things about microfluidics in this particular case is that because you have really small length scales on the order of microns, you have a fairly fast diffusion, and which is very essential in these biological reactions where you have, say, an antibody and antigen. You want fairly quick time scales, and since only diffusion is helping you out here, you want the diffusion to happen over a reasonable time scale, let us say in the order of minutes and not hours. So by reducing the length scale, you definitely have that sort of advantage in terms of having faster equilibration.